Okay. Hi. Yeah. Hi, people. Good. Welcome to the session. Are you guys able to hear me? Hello. Hi, Ashish. Yeah. Okay.
Hi, we can hear.
Good. Yeah. So, welcome to this session. Where do I minimize this? Okay. Okay. So, this is basically the starting session for data structures and algorithms. It will be just introduction, and I guess you guys have already seen the contents which Anup shared earlier. Uh, okay, so before we begin the session, can you guys like get a paper and a pen and write a simple program to find the Fibonacci number? And you guys know what a Fibonacci series is, wherein a number is equal to sum of previous two numbers. So this is an example of the Fibonacci series. The first being 0, second being 1, third is equal to second plus first, fourth is equal to second plus third, and so on. So basically, this is the function signature, wherein the name of the function is fib, return type is int, and there is a argument int n. So in case I pass 0, I want something like this. Fib of 0 is equal to 0, fib of 1 is equal to 1, 2 equal to 1, 3 equal to 2. I'll just give 2 minutes, get a pen and a paper, try to write the program. And you should let me know in case you are done. Balaji, probably some issue with your speaker because I think others are able to hear. Fine. 2 minutes done. Did someone write the code? Anyone? Hello. So at high level, we can generate a series of the Fibonacci numbers and then return nth. Oh, you mean taking an array and then storing the Fibonacci numbers of all the for all the indexes and then returning the nth, right? Okay, fine. We'll come back to that. Yeah, good. Okay, coming to the important topic, why data structures in algorithm. Uh, they are important because they are what you do after you have become a computer scientist. Without data structures and algorithms, you will only be a monkey coder. I read this line somewhere in Quora, and it's like I like this line a lot. It While I was in IIT Delhi, I was part of training and placement cell, wherein I used to interact with a lot of big companies and senior people from the big companies. And at some point of time, I asked one of the top person in one of the senior CS companies, and I asked him, "Sir, why data structures are so important in computer science?" And this is what he mentioned. Data structures are not important in computer science, they are computer science. And the third is like my own line, how can you be a good coder Hello? Okay. The third most important thing is how can you be a good coder if you don't know how good your code is. I have seen people believing DSA is like an advanced concept. This is not an advanced concept. Rather, I believe DSA is the most basic thing which you guys need to know if you are working in any of the IT field. It's the most basic thing, and it's being used in real world a lot. We people use Google Maps a lot, and they use graph algorithms extensively. If we use computer science, we use computers. There is something called as process scheduling, which you guys must have heard when you did your BTech and MTech. Priority queues are used a lot in your process scheduling. Even a simple text editor uses a lot of data structures. When you write some incorrect sentence and you see a red line below that incorrect word, and you see a red line below that word, that's because your text editor is using something called the dictionary data structure. It's called as tries, and not just the incorrect, just the red lines. You even see a lot of suggestions for that particular word, the correct words. That is being done by something called as edit distance, a part of an algorithm in dynamic programming. And there are other cool stuff which happens in day-to-day life, but you don't appreciate data structures much. And last but not the least, why you should learn data structures. uh, Even though data structures and algorithms being the most important thing in computer science, but even then, more than 90% of the IT people don't even know the basics of DSA. So this is what will differentiate you from the huge IT crowd. And the most important thing is, if you want to switch a company, go into product based companies. All the good product based companies will interview on this. I've mentioned four. There are lot more companies. Okay, so this is what we are going to cover today. Why data structure in real world we have already covered. Uh, there is some stuff which I need you to understand even before starting data structures. I'll quickly go through those memory segments and understanding objects plus references, how objects are instantiated, where does they get stored, how they work, blah blah blah. Then I'll go to time complexity, space complexity, and introduction to linked list. Okay, these are some of the ground rules. I sometimes speak really fast. This is what I've got the feedback from the previous sessions. You should let me know and ask to repeat. Any point of time you have got any queries, stop me and ask. In case you are able to understand what we are discussing, please. Or reports and uh, to be clear. Okay. In case you're able to understand what we are discussing, please acknowledge. Helps me to better control the class. Yeah. You can speak, you can message in the chat box, both ways is fine. But please acknowledge. Please reply to my questions. Yep, thanks. Thanks, Jay. Okay. Coming to the memory segments. So your RAM, the primary memory, is basically visually divided into three sections. One section is called as stack, one is called as heap, the other is called as code area or the text section. So all your local variables get stored in this part of your memory. Okay. So when you write int a in your program, this a actually gets a space in the part of the memory called as stack. When you instantiate a new object, you use the word new. So I'm using Java terminology, use new. Even in C++, new works. Okay. Or in case of C, you can write malloc. You write these keywords, the space is being allocated through a part of the memory called as heap. All your static variables and your global variables get stored over here, the third area, code area or the text section. So in nutshell, all your compile time memory, your static variables in stack, your runtime variable in heap, and all your static and global variables goes in the third part. Okay. So if you write something like this, class my class, wherein your class has got a single variable, and this is your main function. In case you write something like this, my class obj1 is equal to new my class. You are basically creating an object of my class, and you're writing obj1 dot a is equal to 5. How does this works? So this is the same code which I wrote earlier. This is stack. I showed you. This is heap. Right. So when you write this statement, my class obj1 is equal to new my class, the obj1, since being a local variable, gets a space in the stack, and when you write new my class, since this is a dynamic memory, this gets space from the part of the memory called as heap. I already told you, and this is how it looks, and you can visualize it in this way. So obj1 is over here, this is the object my class, and this object has got a variable a which is being assigned a value is equal to 5. So obj1 is not the object, obj1 is just like name of the object, or you can say obj1 is the reference to that particular object, or in other words, it's actually storing the address of my object, or I can say it's pointing to that object. So all those things means the same. Obj1 is just pointing to an object which is holding a, and the value of a is equal to 5. Now further, if you create a new object and you write obj2 is equal to new my class, in that case a new object gets created in the heap, a new reference in the stack, and then now this is pointing over here, right? And when I write obj2 dot a is equal to 7, obj2 dot a, this a gets value is equal to 7. Okay. And then lastly, if I write obj2 is equal to obj1, that actually means whatever address obj was holding, now that will be copied to obj2. In other words, the object wherein obj1 was pointing, now obj2 will point to the same object. So kind of like this. So this pointer, it's broken, and now obj2 is pointing to the same object wherein obj1 was pointing. So now if you write obj2 dot a is equal to 8, this actually will change this thing, not this. This is something which is really important, and you'll appreciate it when we'll start linked list. Okay, ignore this. Okay. So coming to factorial or even Fibonacci. So I asked you guys to write a Fibonacci program to get the nth Fibonacci number. These are two ways. There can be multiple ways. One of the ways which Abhishek was mentioning, even that is the correct way. But I've written two ways over here. I can even write the same code in 4 or 5 different ways. When there are two ways I've written over here: int Fibonacci, int n. This is a recursive way wherein I'm simply, if n is equal to 0 and n is equal to 1, I'm returning n. Else I am adding previous to recurrence calls, and I'm returning that stuff. Right? There's one more way which is an iterative way wherein I'm using 3 variables a, b, and c, doing some stuff and then returning the value. Okay. Can you guys tell me which one is better? Iterative is better. How? How you can speak?
There is no repeated calculations.
Oh, okay. Good.
Hello?
I'm able to hear you. Yeah. Repeat
There
it.
is no repetitive calculations because in recursion we repeatedly calculate the same thing again and again.
Recursion complexity is more. Iterative will take more memory. This is interesting. Okay, we'll see all these things. in detail. Okay, so coming to the factorial program. Coming to the factorial, now these are two ways to write the factorial, again an recursive and iterative way. N equal to n into factor of n minus 1, and over here I'm doing some stuff and then returning the actual value which I've got, right? We will discuss which is better, recursive better, iterative better, more space, more memory, all things we will discuss. Okay, coming to time complexity, right? So we just discussed two ways to solve a particular program. We wrote two programs to get the factorial, we wrote two programs to get the Fibonacci. In real world this usually happens. You're given a problem, there can be multiple ways to solve that problem, okay? But how will you know which way is better, which algorithm is better? So there's one way by which you can do it. That's like uh, write both of those programs and then run both of them and see which one is faster. I don't think it's a good way, because you can still do this thing if your program. So one program suppose takes 3 seconds, other one takes 4 seconds. With some probability, you can say first one is better. But in case you are working in uh, so I have my research work was in NLP and machine learning background, wherein we used to write programs which used to run for days. Now in that scenario, I cannot write two programs and run one program for 5 days, and then second program will take 6 days, and then I'll say, oh, first program is better, it took 5 days. It's a really bad thing to do, not scalable, not feasible, and in case you are doing this thing, you're really wasting your time. Right. So time complexity gives you that power to compare two algorithms or multiple algorithms without even the need to run them. It's kind of a theoretical concept wherein you don't even need to run those programs. You do not even need to worry about the underlying architecture or the processor or anything which is like, or your system, your processor, your memory, and blah 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 blah. It's a theoretical concept. Even without knowing the configuration of your computer, you can tell which program will run faster and which will be bad, right? You can think of this like number of steps the program will take in terms of the input. I'll do the examples later. Time complexity is usually denoted by one of big O, something called as big O, big omega, and then theta, right? We'll again do all these things in detail later. I don't want to go into too much theoretical part at this point of time, but for now you can just assume time complexity gives, not assume, you can just note that time complexity gives you the power to compare two algorithms without even need to run them. It's a theoretical concept, and this is what is uh, the mostly used denotion, and we'll even discuss why. Right? And it's kind of a number of steps the program will take in terms of the input. To give you an example, consider this example. So what is a simple program wherein you're doing some stuff, it's a single statement written over here, and this loop is running for 5 times, right? So suppose this thing takes one step, then the total number of steps which the program will take will be equal to no message, and yes, will be equal to 5. So over here, in case if I discuss about this example, it's a single step again. We're running it for n times. It will be n steps, right? And over here it will be 2n steps. I will really appreciate if you guys give the example answers and even let me know if there is any issue in moving fast, moving slow, blah 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 blah. Okay. Okay. So we discussed these three. This will be 5 steps. This will be n steps. It will be 2n steps, right? So over here it will be, now please take out a pen and a paper. This will be like it's not like the session is not like even only I am speaking and you're just hearing. You'll have to actually get out a pen and a paper and do some exercise as well. Data structure is not just listening, it's like math where you need to practice. I got one answer as n by 2, fifth is n. Let me write down the answers. N by 2, so they said this is n by 2, this is this, and then fifth is n square, fourth is n into n plus 1 by 2, fifth is n square, fourth is n by 2, fifth is log n. Oh, good. Fifth log n, sixth is log n. Oh, say fifth is log n. Sorry. Plus 1 by 2. Okay, good. Yeah. I'm good. One answer. 2. Okay, so let's discuss. Yeah. Over here in the fourth example, and at any point of time, so this I say this to everyone, even when I used to teach fourth class mathematics, I used to say the same statement which I'm saying now. At any point of time, if you're confused, you should simply take examples and you'll get the answer. Okay. Even if you are solving a simple fourth class mathematics problem wherein you need to find out, wherein the problem is if 5 bananas cost 10 rupees, how much 10 bananas will cost. You can just simply take examples and you'll get the answer. So over here, in case suppose n is equal to, so n equal to 8, right? So this will first run for I is equal to 0, then it will run for I equal to 2, then it will run for I equal to 4, then it will run for I equal to 6. So it ran for 4 steps, 4 times. So suppose n is equal to 4, it will run for I equal to 0, I equal to 2, 2 steps. So n equal to 16, it will run for 0, 2, 4, 6, 8, 10, 12, 14, 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 steps. It's really simple. 8 goes to 4, 4 to 2, 16 to 8. That means n by 2. Right. Over here, we can simply take examples, or you see it's a nested loop, right? So for each I, this is basically, I should write it like J, I is not correct. For each I, it will run for n times. So for 1, it will run for n times. If it's 2, it will run for n into n square times. And since there is no confusion, it's n square. Over here, again, you can take examples. So suppose n is equal to, the same examples I took earlier, n equal to 8, it will first run for I equal to 1, then it will run for I equal to 2, then it will run for I equal to 4. It will run for 3 times. If n equal to 4, it will run for I equal to 1, it will run for I equal to 2, that means 2 times. If n is equal to 16, it will run for I equal to 1, it will run for I equal to 2, it will run for I equal to 4, it will run for I equal to 2, 8, that means 4 times. And in case you guys have any confusion, you should let me know. This actually maps to log n. And in computer science, if we don't write the base of the log, it's actually 2. Whenever the log base is 2, you don't actually need to write the base. In computer science, we have mutual understanding, all the computer science engineers, that your base is by default 2. And so similarly, if you are working in physics and you don't write the base, so all those physics people have the understanding that the base is 10 by default. But in case your base is something else than 2, you should definitely write the base. Okay. So these are some of the categories of the time complexity. Okay. So constant is usually denoted by order of 1. Sorry. So wherein it's a single step, or I can say the number of steps. This is how you usually write number of steps does not depend on input, or I'll say n, right? So that means in this example, since I wrote 5 steps and it's not depending on n, I can write it is order of 1 or constant. Logarithmic order of log n, like this example, linear is order of n or n to the power 1. Polynomial is n to the power a, where a is a constant. Even linear is polynomial only, where a is equal to 1. Exponential is a to the power n, where a is constant, like 2 to the power n, 3 to the power n, 4 to the power n. And there are some of the rules which you need to understand. When I write order of n plus 2, that is actually equal to order of n. We do a lot of approximation in time complexity, and we'll discuss all those things when we'll go into the theory of time complexity. I don't want to go into, I usually don't go into that much theoretical stuff in the first class. The class becomes too much boring. But I will definitely go in the details, probably in the today's class, or maybe in one of the next sessions. Even not even multiply, not even addition. Even if you are multiplying n with some constant, you can write order of n. Even division, order of n. Whenever you have two time complexities in addition, order of n plus order of n square, the bigger one uh, dominates. But in case of multiplication, it will actually be equal to order of n cubed, right? So you should let me know if there are any doubts. So going by these rules, I can write this to order of n. I can write this to order of 2n, but again, I don't worry about constants. It will be order of n. I don't worry about constants. This will become order of n. This will be order of n square. This will be order of log n. Good, yeah. So going by these rules that we have discussed now, can you guys tell me the time complexity for this thing? Fast. I need to reply. This is a single program.
Order of n square.
N square, right? So how come this is n square? This part is actually order of n steps or order of n. This part is order of n square. We have discussed. So that means the total. Oh, this is a single program, not two multiple programs so much. So this actually will be equal to order of n plus order of n square, or I can say order of n plus n square, or I can say order of n square. Good. In case of any doubts, you should let me know. Else, I'm assuming everything is going fine, and I'll move forward. So coming back to our previous factorial function, when we started, we started with this. We have got two factorial programs, and we wanted to calculate the time complexity for that particular program, right? So coming back to this thing, now we have discussed how to calculate time complexity. We have discussed what time complexity is. We may have not gone into the too much theoretical stuff of the time complexity, but we have some idea what time complexity means and how to calculate time complexity, and how can you compare two algorithms with the time complexity, right? So it's really visible over here. So in case your one of your algorithm is this and other algorithm is this, you can simply say this is better because this is order of n and this is order of n square, and we all know order of n square is more than order of n. That means fifth is better than fourth. My writing is not that good. You should let me know in case you're not able to understand anything I'm writing over here. Fortunately, in computer science, writing does not matter. We need to write the code. Yeah. Okay, so we know we have some idea about time complexity, right? So coming back to our previous problem wherein we started with factorial, we wrote two programs and we wanted to see which one is better, right? So now talking about this program, what will be the time complexity of this particular program? Tell me. Linear, good. Good, linear. It's the same thing, right? So we are running our loop for so we will actually it'll be something like, if I count, this has to be one step, this is one step, this is one step. So this is like 1 plus this step will run for n minus 2 number of times approximately, n minus 2 plus 1 comes out to be n, or I can say order of n. But even if it is n plus 3 or n minus 3 or something, you can simply approximate it to order of n. We have discussed this thing already, right? So this program will run in order of n. Good. Now, can you just tell me the time complexity for, we are actually comparing the two algorithms, right? This is where we started. Now we found the time complexity for this thing. Now, what will be the time complexity for this particular program? Balaji wrote n factorial. No, there is not n factorial. She wrote linear. Balaji, take examples. I told you, right? So whenever you're confused, you take example and you see how it's working, right? Let me take an example. Suppose n equal to 4. So if n equal to 4, I'll call my function for n equal to 4. I'll come to this line. If n is equal to 0 or n is equal to 1, you return 1. N is not equal to 0, not equal to 1, n is equal to 4. This will do this. Now f of 3, it's a recursion call. Not n square, not n factorial. Nops, 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 nops. And we'll see how it's really easy to find out. Ashish, I know it's order of n. We have been writing it again and again. Yeah, good. Okay. So this will actually be like something like this: 3 into f of 2. This will call 2 into f of 1, and this will be then. Oh, you don't need to call it further, right? This is how your program will work, right? And we'll see. Wait for a second. Okay. So time complexity for iterative programs, it's easy to find because we have just tried it out. But I can see people are having confusion while finding the time complexity for recursive programs, right? And I have seen this in my previous classes as well. People usually have confusion. Iterative programs really easy to find. Just the number of steps. If there's a for loop, multiply it and blah blah blah. If there's a recursive program, it's really difficult to find time complexity for that particular recursive program. So this statement will actually help you to find the time complexity for any of the recursive programs, right? Time complexity of a recursive program is actually equal to number of function calls into time complexity of each function call. And when I say time complexity of each function call, over here you accept the recursive call. It's a really simple line and it really helps you to find the time complexity of any of the recursive problems. To give an example over here, Okay. So over here, I wrote, I'll go over here. Okay. So I wrote time complexity of a recursive program is equal to number of function calls into time complexity of each function call except the recursive call. Right? So we wrote a factorial function fact int n int I wrote n is equal to 0 or n is equal to 1, return 1, and then I wrote return n into set of n minus 1. Right? So there are just two things I need to find. One thing I need to find is how many number of function calls will be there, and then I need to find the time complexity of each function call except the recursive call. Right? The second thing is really easy to find. Right? So if you see this program has got how many steps? This is just a single step, one step. This line actually is doing two things. One is multiplying and then calling the recursive thing again. So we are actually ignoring the recursive call, right? I'm not taking the recursive call into consideration. So if I see this is again one step only, right? So I can say 1 plus 1 2 steps, or I can say it's again order of 2 or order of 1 constant, right? So that means this part, the second part, is actually constant, just order of 1, right? So the second thing which is left is now you need to find number of function calls are there, how many more function calls are there, and the first and this thing is like can be easily find out if you take an example. So the same example which I took earlier, right? So if I took f of 5, so f of 5 actually called f of 4, f of 4 called f of 3, f of 3 called f of 2, f of 2 called f of 1. So in case n is equal to 5, how many number of function calls are there? 5. In case n will be equal to 10, how many number of function calls will be there? 10. And equal to 15, there will be 15 function calls. So that means this number of function calls is actually equal to n. Whatever the n is, number of function calls will be equal to n. And then there's a multiplication sign in between. So that means this actually comes out to be order of n into order of 1, or I can say order of n into 1, which is equal to order of n. So that means the time complexity for this program is equal to order of n. So we started with a problem. We wanted to find factorial of a number. We wrote two programs for that, one recursive, one iterative. We wanted to compare those two programs. We discussed time complexity to compare those two programs. Time complexity for an iterative program, time complexity for a recursive program, and we eventually again have the same confusion because the time complexity for these two programs are actually same, order of n, order of n. Right? Now which is better? The complexity is same, which is better? Ashish J, Balaji, Sanoj, Rahul, they are more people. Bhargav, which is better? Murali, Chandrasekhar, Romil, are you guys listening?
Can you repeat your questions once again?
Yeah, sure. So this is where we started. We started with a problem to find the factorial of nth number, right? And we wrote two programs for that. One an recursive, recursive way, and other iterative way, right? And we wanted to compare those two programs, those two algorithms, without even the need to run them. Therefore, we went and studied what a time complexity is, and then when we studied time complexity for iterative program, we studied how to calculate time complexity for recursive program. But eventually we found that the time complexity of both those two programs are written over here happens to be the same. They are both order of n. So I started with the problem. I wanted to see which one is better, but even after studying time complexity, I don't know which is better because they both have the same time complexity. So the question: do you guys know which is better, or can
I
you?
think both are the same. I mean,
The time complexity is same for both of them, but which program is better?
That I will see that tell that factorial program is better.
Sorry.
Because as you tell that if you see that the first one in
Hmm.
fact n, here we are seeing that uh, the way it's happening that if you see that it's fact, if it's the n, it will go factorial of n, then factorial of n minus 1, n minus 2, like that. If you
Mm-hmm.
sum up of all these things, it will come on factorial of n. But if you go for the second one, it's like it's a even it's a uh, time complexity of O and N, but it's a combination of many of adding of this. It like if you see the first line int let equal to 1, it will go for n1, and then sorry, yeah, the second one it will go under the loop, that is, and then and again one more line of it is there. So its addition is little bit more number of iteration will be happen over there. So in this case, I may suggest that this first one is the better one.
If you go by number of steps, they both have the same steps, approximately the same steps, because we do a lot of approximation when we are studying calculating time complexity. Okay. If we go by code cleanliness, your first one looks more clean, just two lines of code, easy to understand. The second one, I'll think and see how come it's better. Okay. Please keep your mic on mute if you're not speaking. If you're speaking, obviously unmuted. If you're not speaking, keep it on mute. Uh, so second program looks really messy compared to the first program. It's really simple, clean, easy to understand. Number of steps are approximately same. This is what my time complexity told me, right? But then there's something which we have not discussed. Time is fine. What about space? How much space my program is taking, right? So this, and we have not studied what the space complexity is, and we'll study what space complexity is, and then we'll come back. Okay. Anyways, before starting with space complexity, let us discuss the time complexity for these two programs. Fibonacci, right? We even had this problem as well. What is the time complexity for this program? Linear. Yeah, it's linear, simple, right? This
It's
is
a
step, one step, one
linear.
step, one step, one step. So it's like 1 plus n into 3 plus 1 comes out to be 3n plus 2, or I can say order of 3n plus 2, or I can say order of n, because we have discussed, we don't worry about constants. Discussed, right? Linear. Order of n, linear. The interesting part. What is the time complexity for this?
It's the same. It's a linear.
So you should take example discussed. In case it's linear, give me the example. How come it's linear?
Just while ago, we have seen that
So I'll give you
this factorial of
the
this, it
same.
was n. So
So
addition of two of the factorial of O of n is n.
I'll give you the same statement I gave 5 minutes back. Time complexity of a recursive program will be equal to number of function calls into time complexity of each function call, and you ignore recursive calls over here. Right, this is what we discussed. So if I see the second part, again, this is single step. I'm just doing addition of some two recursive calls. I don't worry about recursive calls, so I'll say this is one. Right. The second part is order of one. What about first part? Let me take an example. So in case I'm finding Fibonacci of fifth number. So f of 5 will actually call f of 4 and f of 3 as well. See this, fib of n minus 1, fib of n minus 2. F of 4 will call f of 3 and f of 2. F of 3 will call f of 2 and f of 1. This will call f of 2, and f of 1. Again, this will call f of 1 and f of 0. This will call f of 1 and f of 0. You guys should let me know. I really appreciate feedback. If you guys think I'm going slow or fast, you should let me know. It's for your benefit only. So in case n is equal to 5, this is how it will grow, right? So if you see, and then you can take examples and see this is approximately equal to order of n square. You can take examples, right? So this is order of n square. Oh no, not n square. 2 to the power n. Yeah, thanks Ashish. 2 to the power n. You can try it in your register, copy pen. It will be something to the power n minus 1 plus something and blah blah blah. But if we do approximation, it will come out to be order of 2 to the power n. And when starting today in computer science, whenever you see a tree growing like this, something like this. So whenever you see a tree growing like this, it's always exponential, 2 to the power n. So each node has got 2 children. It's 2 to the power n. And whenever you see a tree like this, each node has got 3 children. And you can take examples and you can convince yourself it's right because I know it's right. Right? So if you see this, that means time complexity for this particular program is actually 2 to the power n, and time complexity for this particular program is actually order of n. And now we know we don't need to worry about the space now because your time complexity is giving you a lot more information over here. In case of factorial, the time complexity was same, so therefore we need to discuss about space complexity. But in case of Fibonacci program, we wrote 2 programs over there. The time complexity itself is telling me that this program is better. And to give you some examples, for example, n is equal to 5. So if n is equal to 5, your second program will take 5 steps, approximately 5 steps. But your second program will take 2 raised to the power 5, which will be 32 steps. In case n is equal to 10, your second program will take around 10 steps, approximately. But your first program will take 1024 steps. So go back home, you're already at home. Okay? Write both of those programs in your computer system, run it for n equal to 100. Your first program may not end because 2 raised to the power 100, it's huge. So this will take 2 raised to the power 100 steps, and this will be just 100 steps. So this program is really bad. It looks simple, looks easy, but this program for your big numbers may not even end. So this is the power of time complexity. Even without running your program, you are able to see how good your program is and how bad your program is. And usually exponential time complexities are not feasible in real world. So wherever you see an algorithm which has an exponential time complexity, those algorithms are not feasible in real world. They cannot end. And there is one thing which is really important. We are discussing about this time complexity and space complexity, and basically we are discussing about this data structures only when we are assuming that there is huge data. There is no point of discussing data structures, stacks, queues, linked list, anything in case your data is small. Because if your data is small, your program, if your program takes 2.1 seconds or 2.2 seconds, hardly matter. I don't mind. Okay, but if there are two program, if the data is huge and your program will take hours or minutes, then it's really important to discuss about this data structures, time complexities, and space complexities. So there is one ground rule which is really important. We discuss about data structures, time complexity, space complexity, and all those things with that assumption in our mind that data is huge. Right. So over here, if I go with that assumption that data is huge, then in case of huge data, this program will never end. It's a really bad program, and this is a really good program. Just order of n. Okay. Anyways, going forward to my space complexity thing. Okay, I don't actually. Yeah, I don't have more slides because I was not that well yesterday. But yeah, I have marker and I can speak. Okay, so space complexity is actually similar to time complexity, wherein we denote it using these these three symbols, big O, omega, and theta. And again, this being the most important, we'll discuss again. I'll discuss this thing later, probably in one of the next meetup sessions. Yeah, this being the most important. So space complexity, as the name says, it has something to do with space. Time complexity with time, space complexity with space, right? And when I say space, I actually mean what is the extra space being used in my program. Okay, and again, just like time complexity in terms of input, because your input is huge. If your extra space is not depending on the input, then you can assume it to be constant. Input, or I'll say n, right? So for example, if I write this program int f int n return n minus 2. Okay, this is a program which is doing something, just return subtracting 2 and then returning the same number which I've got in the input. Time complexity, we know for this program is equal to constant. It's just one single step, and that step is not depending on the n. So even if your n is 100, it will just 2 minus 2. It's not depending on n. There is no for loop, there is nothing, no recursion code I'm doing over here. Talking about space complexity, right? So let me break this single line into two lines. Let me write something like this: int a is equal to n minus 2, and then return a. Right. So over here, what is the space I'm using? Extra space. So this I'll not consider as a space, because this is my input. I don't consider input in my space complexity. This is really important, and I have seen people getting confused with this thing. Input, considering input as the space complexity. I've seen many people taking interviews. So you should not worry about the input. Don't worry about the input while calculating space complexity. Just see whatever you are creating to help your program, right? So over here, you're creating. This is what you're creating. You're creating a variable. So in case it's Java or any language, it will take approximately like one int take 4 bytes, for example, right? So it will take around 4 bytes, right? So in your whole program, the only space you are using is 4 bytes. And this 4 bytes is not depending on the input, right? Even if your n is 1000, you will use 4 bytes. Your n is 10,000, you will use 4 bytes. So I can say order of n, order of 1, sorry, okay, or constant. So I'll say space complexity for this particular program is constant. I'm not using an extra space. So time complexity is constant, space complexity is constant. Let me take more examples. I need more slides. Okay, let me take more examples. Fn int n for int I equal to 0, I is less than n, I plus plus, n plus is equal to I, return n. Now I'm writing a couple of programs over here. You guys take out a pen and paper, just write the time complexity and space complexity for all those programs, and we'll discuss. This is one program. The second program is int fn int n return n dot length minus 1. Second program int fn 2 3 1 int n int k equal to new n return k of 0 equal to n return k of 0. So I wrote three programs. Let us discuss about the space and time complexity for these three programs. You guys ready with the answers? You need to tell me the answers now. Okay, order of n, order of 1. Okay, this is time complexity, space complexity. Let us discuss time complexity first. So time complexity for this thing, order of 1. No. So time complexity for first
N.
n. Time complexity for this thing, 1 is n,
1.
2 is 1. For this thing, 1. Okay. You
Constant.
guys should let me know if you're not understanding, not going with the class, right? So overhead time complexity, this is order of n. And we have done enough examples, and we know this is running for n times. So it's like order of n steps, or I can say order of n. There is no for loop, nothing. It's just a single step. I'll say order of 1. So there are again 3 steps only. 1 plus 1 is equal to 1 plus 1 plus 1 is equal to 3, and then 3 I can write order of 1, so it comes out to be constant, right? It's really easy, right? So let me talk about space complexity. What about space complexities? And again, when
First one is N.
first one is n, second
Constant.
is constant, third
N.
Constant.
n or constant. Yeah,
Constant.
I even see
N. Third is N.
space constant linear. Someone constant linear. That means it order of 1. Anyways, we'll discuss, right? So space complexity, I have been telling you, space complexity is the extra space which you are using. So to find space complexity of any program, just see what all new variables you are creating in your program and see whether that variables are depending on the input or not. So over here, there is one variable I have created which will take 4 bytes. Even if your n is 1000, your n is 1 lakh, I am just creating one variable. It's not depending on n. That means I can write it's constant. Constant means not depending on n, not variable. It's constant. Whatever your input is, it will still take 4 bytes. Therefore, it's order of 1. You go with second program. Over here, you see there is this thing, right? An array. But this is which is given in the input. In a program, you're not creating any memory. Even if I write this into 2 steps, something like this, in k is equal to this, and then return k, even then there is some memory, 4 bytes, which will be same irrespective of the input, right? So it's order of 1. But if you see this program, so over here, please keep your mics on mute if you're not speaking. So over here, you're creating a new array, right, of size n. So that means if your size n is 2, there'll be array of size 2, and it's an integer array, right? So if your array is size 2, this is 4 bytes, this is 4 bytes, 8 bytes. If your array of if your n is 5, there will be an array of size 5. So that means 5 is equal to into 4, 20 bytes. So this is like something like n into 2 bytes, something like this, right? And into 4 bytes, right? So if you see, this is actually increasing in terms of n. So if your n doubles, then your space required will be double, right? So your space is actually proportional to n. If your n doubles, your space double. If your n quadruple, your space will quadruple. Or in other words, I can say it's order of n. So space complexity over here is order of n. Even though you're not using this space, hardly matters. You're creating a new space. So whatever space you're creating, accounts to your space complexity. Right? Good. Any doubts? You should let me know. If you're able to understand, you should let me know. So coming back to your factorial program, like this is where we started. I'm again moving to the previous problem, to the initial problem we started with, right? So let us calculate the space complexity for this thing now. What is the space complexity for this thing? Constant. So if you see, this is one variable I have created over here. This is second variable I'm creating over here. They both are integer. They'll total take 8 bytes. But then again, if whatever your n is, they'll take 8 bytes, right? So I can say space complexity for this thing is constant. Coming over here, space complexity for this. This is interesting. Space complexity for this n. So if you see, you're actually not creating a new variable over here. Even if I break this thing into 2 lines, just like I have been doing earlier, int k is equal and return k, it's just a single variable, right? And it will take 4 bytes, whatever your n is. So this looks like constant, but it is not actually constant, and we'll discuss why. It's the most important thing, one of the most important things, right? Before discussing how to calculate space complexity for this thing, there is one concept which I need to tell you, again kind of like pre-DS stuff, right? So I started with memory segments. This is where I started, right? And I told you all your local variables goes over here, or your dynamic memory, whenever you use a new keyword, or your static fixed thing goes over here, your global, so by static I actually means fixed, your static variables, the keyword static, they goes over here, global goes over here, right? So for example, your program is something like this. You have a main function, and inside that main you have something called as like int a is equal to 2, and then you're calling some function f. This is your f function, returning anything, not returning hardly matters. This has got something called as int a is equal to 3 g. This is g, and then g has got probably again its own a is equal to 5. And then suppose this is a program, it's doing something, I don't know what, but this is your program. Your main function is calling some f function, your f function is calling some g function, and then obviously it comes back. So when this executes, it comes back over here. When this executes, it comes back over here. This is how your flow goes, right? We know this thing. And since this a is a local variable, even this a is a local variable, this a is a local variable, they all should go into this part of the memory. We have been discussing this thing, right? So, but how will your processor, your underlying system, or in case of Java, how will your JVM or any language, it'll understand the difference between these three variables? How will they actually get stored in the stack, right? So whenever you create a new function, so it's not only about the local variables which get stored in the stack, your complete function gets stored in the stack, right? So, and something so whenever you create a new function, or basically whenever you call a new function, whenever function is being called, that complete function gets stored into the stack, and the name of that thing is actually called as activation record. I don't know whether you have heard of this terminology or not, but so activation record is just the record which is being stored in the stack whenever a new function is being called, right? So that means when your program starts and main function gets called in your stack, suppose this is your stack, an activation record of main will get stored over here, activation record of main, and what all variables which are local to this particular function will be over here. and then main called f, right? F. So f will be stored on top of main. This is activation record of f, and then it will have one a over here. Now f is calling g, so g is being called. There will be an activation record of g which gets stored over here, and this will have its own a is equal to 5. Now if suppose g is calling something, that will get stored on top of g, and then when g completes execution, f will start execution. So if you see internally, it is actually behaving like a stack of books. So wherein you one book gets placed on top of other book, and then if you want to take one book out, you have to start from the top. You cannot remove one book from the between. It will fall, right? So this is how it works. It actually works like stack. Therefore, it is being called as stack, named as stack. And this is how actually your flow goes, right? So main will call f will call g. When g completes, comes back to f. When f completes, comes back to main. This is how we understand that flow works. But this is how it is being actually implemented in the memory. This is how your processor, your system knows where to come back. Your G completes execution. It knows it needs to come back over here. This completes execution. It knows it needs to come back over here. Right? This is how your stack grows, and this is how your stack uh, basically this is how it pushes and pops from the stack, right? And this stack is actually fixed. It's not something which like you do not have all the memory in the world. There are things are fixed, right? So I'm using this space. So suppose you have a function like this in f, right? This is a recursive call wherein there is no base condition. I'm missing a base condition over here. Base condition missing, right? If you write this program, if you execute this program, how will this work? There will be a stack. Suppose main some main is calling this f, right? So there will be a main activation record. There will be an f activation record. Now since f is again calling f, even though they are the same functions, but activation record is created every time a new function is being called. It's a new function being called, even though the signature is same, even though the function is same. There will be a new activation record created over here. Now again, f is again calling f. There will be an activation record over here. F is calling f, activation record over here. Now I told you, right? This is a fixed space. At some point of time, this will full. And I don't know whether you guys have seen this thing or not, but it's a really common error which people usually get, called as a stack overflow exception. And this is what stack overflow actually means. You can easily test it writing a recursive program without a base condition. You will definitely get stack overflow exception. Because stack is full, you're not stopping it. The new activation records being created every time a new function is being called. And this is how things work in your memory. This is how function calls works in your memory. This is how local variables actually get stored in the memory. And this is how recursion works, basically, in a nutshell, right? Any doubts, you should let me know. No message. No new message. Moving forward. So where were we? We were finding space complexity. It's really messy slides. I need to be better while managing my slides. Anyways, yeah. So this is not order of one, right? I'm coming back to the same problem. We started this problem more than 1 hour back, and we are again at the same problem, right? We want to compare these two programs. We want to know which is better. We have studied time complexity for iterative, time complexity for recursive. We studied memory segments, objects, how things work, lot of things. We studied space complexity for iterative programs, but we are still not able to answer which program is better. Right? So over here, if you see, again going back 10 minutes, 15 minutes, if you see space complexity looks constant over here because there is no new extra space which we are creating over here. we are even if I write it in this way, we are using 4 bytes, but that is not depending on the input, and so I can say it will be constant, not in terms of n order of 1. But this is not actually correct, because I just told you whenever the new function call is being whenever new function is being called in your stack, in your memory stack, there is a space taken to actually store that particular function call, right? So even though it is not visible over here, but there is a space which is actually being used in your stack. There's a space which is actually being created in your stack, right? So in case I'm using maybe I'll go to the new slide. So in case I'm calling for f of 5, right? So this is, suppose this is my stack main, this is my main activations record. Main will call f of 5 because my n is equal to 5. Now f of 5 will call f of 4, but this is how I wrote my program, right? Factorial f of 4 will call f of 3, f of 3 will call f of 2, f of 2 will call f of 1, and something like this, right? So this much space my program has actually taken in your program's execution stack, which is not, even though not visible in your program, but this space has actually been taken, right? And this is an extra space, because this space is not being not needed if we discuss about this iterative program, right? So that means an extra space, and we need to count this extra space. So in case your program is a recursive program, you need to worry about that space as well. And again, just like I told you, space time complexity for recursive programs, the space complexity for recursive program is actually equal to maximum height of stack into space complexity of each function call. And again, just like space time complexity, we ignore the recursive calls over here, because we are anyways considering recursive calls when we're talking about stack, right? So again, so in this program, so in this program, in this recursive program, the space complexity for this program looks like to be order of 1, because there is no extra space which is being used. So that means the second part, this is order of 1, but your first part is actually order of n. If your n is 5, then we're using 6 space, 5 plus 1 hardly matters. So I can say n plus 1 or is equal to order of n, hardly matters. We do a lot of approximations. Again, we'll discuss that thing. I don't think we have time today, but in some other lecture later. But we do a lot of approximations, right? So order of n, order of 1. And when I say we'll discuss, I usually whatever I say I discuss. So it's actually order of n into order of 1 comes out to be order of n. Right. So coming back to my same problem. So time complexity for this is order of n, and even space complexity is order of n. We have discussed why. Time complexity for this thing is order of n, but your space complexity is order of 1. And now we know this is better. Should let me know if there are any doubts, else we'll move to something new. This is the complete story of how to calculate time complexity for iterative program, how to calculate time complexity for recursive programs, how to calculate space complexity for iterative programs, how to calculate space complexity for recursive programs. And when I'm teaching whatever topic I'm taking up, be it greedy, dynamic, be it linked list, be it stack, queue, for each and every program we write, I discussed the time complexity and space complexity for each and every single program. So people really become expert in finding time complexity and space complexity just by looking at the code, because we have that much practice. And we can do the same thing for our these two Fibonacci programs, right? Even though we know this is better because time complexity is order of n and time complexity is order of exponential overhead per n over here. But just for our practice, we can still calculate space complexity for these two programs, right? So what will be space for this thing? Sleeping. Hello, morning.
It will be constant.
Be constant, right? So we are creating some variables over here, but 8 by 8 still does not depend on the input. Will be constant. So discuss about this. The space complexity. Now again, it's a recursive program. We need to so recursive program space complexity for recursive program will be equal to number of function calls into space complexity uh, for each function call into number of into maximum height of the stack, right? The execution stack. So space complexity for this thing looks constant because I'm not creating something which is depending on the number of variables, which is not depending on the input. But the interesting thing is how many number of function calls will be there. Basically, the maximum number of stack will be there, maximum height of stack. Got the question, right? Answer. So fib iterative, fib recursive, time complexity I discussed, order of n, space complexity I discussed, order of n or 1 what did it. Order of 1, time order of n, over here time order of exponential, time exponential. What about space? You guys have the answer now?
I think same 2 power n.
Any other answers? It's wrong.
This is O of n into n plus 1 by 2, so order of n square.
I got one answer. Anshul said order of n. Anshul, you want to explain? It's actually order of n. Want to explain? I don't know. You want to explain? Anyways, yeah. So whenever, I told you, right? You always take the examples. You take examples, right? So suppose your n is equal to 5. Okay, no problem. N equal to 5, right? So suppose you want to calculate fib of 5, right? Please keep it on. You're not speaking. F of 5 is calling something like this. We already drawn this in some, not something which is new, right? And so on, right? So how will this actually execute? It will take 10 minutes. How will this actually execute? Okay, how will this actually execute, right? So this will be main function over here. Main will actually call f of 5, right? And then f of 5 will call f of 4. F of 4. F of 4 will now actually call f of 3, right? F of 3 will call f of 2. F of 2 will call f of 1, right? F of 2, f of 1. Right? When f of 1 completes, right? When this gets completed, it will call f of 0. This is not which is running parallelly, right? This is how your program runs. If so one function will get called and then second will get called, right? So f of 0 will come over here. When f of 0 completes, f of 2 will complete. F of 2 will complete. When f of 2 completes, f of 3 will call f of 1. F of 1. When f of 1 completes, f of 3 completes. When f of 3 completes, this will call f of 2. When f of 2 completes, f of 4 completes. When f of 2 completes, f of 4 completes. When f of 4 completes, this will call f of 3. F of 3 will call f of 2. F of 2 will call f of 1. F of 1